My name is Chanzi Hassan Musisi, and I'm going to talk about frequency division multiplexing and multiplexing generally. My serial number is 217022320. Frequency division multiplexing is among the techniques of multiplexing. Multiplexing is a set of techniques that are employed in simultaneous transmission of signals or multiple signals on one data link. Multiplexing is generally a technique that combines different signals into one composite signal, then be transmitted over a given link. Frequency division multiplexing, on the other hand, is an analog technique that is employed in scenarios where the bandwidth in Hz of a given link is higher than all the signals that are to be transmitted over it. So in this case, remember, each sending device modulates or each sending device has different carrier frequencies or modulates different carrier frequencies. These modulated signals then are combined into one composite signal that is transmitted over a given link. That is frequency division multiplexing. Wavelength division multiplexing, on the other hand, is also an analog technique but this time is employed on a different medium, which is optical fibers. So what means is this, what is involved in this is optical signals. Remember, optical fibers have a higher data rate as compared to metallic medium. So using one signal on such a link will be wastage of such a resource. So what wavelength division multiplexing does, it combines different optical signals into one composite signal that is transmitted over that higher data rate medium, which is optical fibers in this case. The next thing is time division multiplexing. Time division multiplexing, on the other hand, is different from frequency division multiplexing and analog division multiplexing. Frequency division multiplexing and wavelength division multiplexing. In this case, time division multiplexing is a digital, unlike those two which are analog techniques. And here in time division multiplexing, time is shared, not frequency, like or bandwidth in frequency and wavelength division multiplexing. So synchronous time division multiplexing is a technique that provides an allotment for each input signal, despite whether it's sending any data or not. It provides an allotment for each input signal in the output, despite the fact that whether it's sending any data or it's not sending any data. The next thing is about interleaving. In time division multiplexing is always visualized as two fast rotating switches. There's a switch at the multiplexing side and a switch at the demultiplexing side. When the switch at the multiplexing side opens a connection, the connection sends an input. What I didn't talk about is time is shared in as an input, and an input is at least 1 bit. So whenever a connection is opened up at the multiplexing side, the connection sends a unit onto the link. Then that opens up, that is what is called interleaving. Interleaving is that process where the multiplexing side, a connection is opened up and it sends an input onto the given line. The next thing is spread spectrum. Spread spectrum is like multiplexing, but this time it's not about bandwidth utilization or bandwidth used. It has a more diverse problems and more complex problems as compared to those of bandwidth. Here we're dealing with wireless networks, wireless media, on unguided media. So in space spectrum, our major aim is preventing access from unauthorized users, which is done by eavesdroppers and other security other security problems in wireless media. So I'm obliged to talk about frequency hop spread spectrum, which is also a technique that uses different carrier frequencies that are modulated by some, but are measured by the same signal. Remember, each time at one moment a signal modulates a carrier frequency, then the next moment it modulates another one. My name is Chandra San again, and I'm going to talk about satellites this time. A satellite network is a combination of nodes that provide communication from one point to another on Earth. And satellite networks are like cellular networks in that they divide the planet into cells, and they can provide transmission capability to and from any location on Earth, no matter how remote. This advantage makes a high quality communication available to undeveloped parts of the world without requiring a huge investment in ground-based infrastructure. Or in ground-based infrastructure may be backbone or internet backbone, which is just like the connection, the major connection of internet from the service providers, from the internet service providers. To look at the operation of satellites, we need to look at a specific term which is called an orbit. For any artificial satellite, remember the artificial satellites and what? The artificial satellites and natural satellites. A moon is a natural satellite which can also be used for relays, but the artificial satellites that can be used to regenerate signals so that signal strength is modified or amplified. So I'm going to talk about orbits for this time. An orbit, I said, for an artificial satellite to needs to have an orbit, which is the path around which it travels around the Earth. The orbit can be either equatorial, inclined, or polar orbit. Polar comes from poles, which the Earth has a north pole and a south pole. So there are three orbits. There is a polar orbit, there is an equatorial orbit, and an inclined orbit, as you can see on my screen. I've talked about in the previous. I talked about different orbits. The first one on top is called. This one is called an equatorial orbit satellite. The next one is called an inclined orbit satellite, and the third one is called a polar orbit satellite. The next thing to talk about is a Van Allen belts. One reason for having different orbits in existence is presence of two Van Allen belts. A Van Allen belt is a layer that comprises charged particles. A Van Allen belt is a layer. I'm going to talk about a Van Allen belt further when I'm talking about categories of what? Of satellites. One scientist called Kepler. Kepler talked about the period of a satellite, which is a function of the distance of which is required for a satellite to make a complete trip around the Earth, and Kepler denoted that period as the period of a function as a distance from the center of the Earth, and period is equal to distance power 1.5 times a constant c, which constant c is denoted as 1/100. The next thing is talking about categories of satellites. The first category is geostationary object satellite. Geosatellites are the first categories I'm going to talk about, and the line of sight of propagation requires that sending and receiving antennas be locked onto each other's location at all times. One antenna may have the other in sight. For this reason, a satellite moves faster or slower than the Earth's rotation is useful for only short periods. To ensure constant communication, the satellite must move at the same speed as the Earth so that it seems to remain fixed above a certain point, and such satellites are called geostationary. To ensure constant communication, the satellite must move at the same speed as the Earth so that it seems to remain at a fixed point, which is called a geostationary or geostationary satellites. Because orbital speed is based on distance from planet, only one orbit can be geostationary. The orbit occurs at equatorial plane. This geostationary satellite employs an equatorial orbit. The orbit occurs at equatorial plane and is approximately 22,000 miles from the surface of the Earth. The next thing is to talk about middle Earth object. This one is positioned between two valence Allen belts. I said a valence Allen belt is a layer that contains charged particles. So the middle Earth objects are positioned between two valence Allen belts. A satellite at this orbit takes approximately like 6 to 8 hours to circle the Earth. Remember, I said an orbit is a path around the Earth. So this middle Earth object that is between two valence Allen belts can take approximately 6 to 8 hours, which is like a third of a day, to circle the Earth. And an example of a middle Earth object is a GPS system, which is abbreviated as Global Positioning System, which is an example of middle Earth object. The other category is low Earth object. Low Earth object is also a category of satellites, but this time it employs polar beats. The altitude is between 500 and 2,000 kilometers with a rotation period of about 90 million to 120 minutes. The satellite has a speed of 20,000 to 25,000 kilometers per hour. Therefore, a low system or a low Earth object system usually has a cellular type of axis similar to cellular telephone system. The footprint normally has a diameter of about 8,000 kilometers because the low Earth object satellites are close to the Earth, and the round trip time propagation delay is normally less than 20 milliseconds, which is acceptable for audio communication. A low system is made of constellation of satellites that work together as a network. Each satellite acts as a switch. Satellites that are close to each other are connected through inter-satellite links. A mobile system communicates with a satellite through a user mobile link, and a satellite can also communicate with an Earth station gateway through a gateway link. My name is Chanzi Hassan again, and the second assignment is talking about orthogonal frequency division multiplexing, intersymbol interference in a digital transmission system, and uniform and non-uniform quantization. I'm going to start by uniform and non-uniform quantization. When digitizing, the first step is to sample the signal at regular intervals. If the sampling time of a sampling or the sampling period is t seconds, then the sampling rate of frequency fs is 1 over t seconds. For a signal to reproduce exactly the sampling rate should be greater than twice the maximum frequency. Quantization gives a finite discrete value to samples. The device that performs quantization is a quantizer, and it takes sampled input and generates the quantized output. The quality of the quantizer output depends on the number of quantization levels. Furthermore, the space between adjacent quantization levels is called step size. So it has two methods. One is uniform quantization and the other one is non-uniform quantization. Uniform quantization has unequal spacing between quantization levels. Uniform quantization has an equal spacing. It has equal spacing between quantization levels. And non-uniform quantization has irregular or ununiform step sizes. So the step sizes in non-uniform quantization is unequal. And the difference between uniform and non-uniform quantization is in which the quantization levels are uniformly spaced in uniform quantization and they are unevenly spaced in non-uniform quantization. That's mainly the difference between uniform quantization and non-uniform quantization. The next thing is talking about intersymbol interference. Intersymbol interference occurs when transmissions are sent across a dispersive channel. In such a scenario, it is possible for the output of the channel intercepted by the receiver to be distorted via temporal spreading and resulting into overlap of individual symbol pulses. One consequence of such temporal spreading is the resulting inability of the receiver to accurately distinguish between different received pulses, and which is referred to intersymbol interference. So I've talked about how intersymbol interference occurs and what it means. The next thing is to talk about orthogonal frequency. Orthogonal frequency is a method of digital signal modulation in which a single data stream is split across several separate narrowband channels at different frequencies to reduce the interference and crosstalk. The original data stream bits that in a conventional single channel modulation scheme would be sent serially, one after the other. Serial means one after the other, are transmitted in parallel, several at one separate channels, several at once on separate channels. That is what they call parallel transmission, but at a lower speed in such a substream within another stream relative to the original signal. This means that the symbols sent in the substreams are longer and spaced further apart than in the original stream. Each bit might be represented by a 1 nanosecond segment of the signal with a 0.25 nanosecond spacing between bits. Splitting the signal across 4 components streams lets each bit be represented by 4 nanoseconds of the original with 1 nanosecond spacing between. This reduces interference among symbols and makes it receive each symbol accurately, maintaining the same throughput like what I've talked about. So that is orthogonal frequency multiplexing, which is also a method of digital signal modulation in which a single data stream is split across several separate narrowband channels at different frequencies to reduce interference and crosstalk.